5 people. You heard that, right? 5. Okay. And we're back. All right, so Allie, Courtney, Riley, Emma, and Enlo.
Okay, so we did the atomic radius periodic trend. The simple definition is an average of how big a specific element generally is, and basically how you measure the atomic radius of an atom. An example is like 2 hydrogen atoms, and you measure the distance from the nucleus to the outermost level, the sublevel, with the electrons, the valence electrons.
And she has a pointer. She's going to model how we're using the laser throughout today.
Okay, do you need it?
No, I got it. So in terms of 2 factors, and every single group is to be mentioning these factors because these are the 2 factors that rule every single periodic trend. For this example, nuclear effective charge, Zeph, as we can denote it, is increasing, is a period trend. So as you go across a period, the nuclear effective charge changes naturally because as you gain protons from, let's say, sodium to chlorine, sodium has 11 protons and chlorine has 17 protons, the strength of attraction the nucleus portrays gets larger. However, as you go across that same period, which I'm looking at like sodium to chlorine, for example, that whole entire period still only has 1, 2, 3 energy levels. So if I have 3 energy levels, the radius should remain the same because the energy levels represent electron clouds. So as that occurs, I do see a difference in radius because the Zeph, the nuclear effective charge, getting larger and larger and larger means it has greater attraction, greater attraction, greater attraction, which causes the electron cloud levels to kind of shrink in towards the nucleus. That whole concept, excuse that for me, Jack can see, is called, basically it is related to the Coulombic attraction that the protons have for their electron shells, or the electron valence shell. So force of attraction is equal to the charge of the nucleus, and as the charge of the nucleus increases, that causes this shrinkage we see across a period. Give us a thumbs up when you guys are good. Thanks. So in addition, the secondary factor that's always talked about in periodic trends is the shielding effect. The shielding effect is basically what we talk about going down a group. So Zeph, or nuclear effective charge, is what we speak of going across a period, whereas the shielding effect is talking about we go down a group. So what's different as you go down a group? You can imagine going from down the alkali metal group, lithium to sodium to potassium, and so forth. Your atom is building itself. Electrons are going to be placed into orbital after orbital after orbital. So as those electron energy levels are added to the atom, there's a lot of space between the nucleus and the last electron shell. So hence the nuclear attraction is diminished as electron shells are shielding the attraction between the nucleus and the valence shell. And so an example of that would be if I have 2, be my nucleus. Okay, so we have a nucleus and we have 1 energy level. Nucleus attracts to, use one. Here, you hold it. Okay, so nucleus, boom! Nucleus attracts very, very strongly to the valence shell. Hold that again. But as more shielding occurs, as more and more energy level shells are added to the atom, there is a shielding, see, it doesn't stick, of the magnetism or the attraction that's occurring between the nucleus and its valence shell. Hence, distance does not make the heart grow fonder. It just doesn't attract. The distance is there. That's due to the shielding effect. We're good. Thanks.
So there are 3 elements that are exceptions to the rule that going from right to left, the atomic radius increases, and that's nitrogen, tin, and antimony, right? Okay, so it's N, Sn, and Sb. And the electron configurations can kind of tell you why that happens. So as an example, starting off with nitrogen, the electrons, the electron orbitals are half filled in the 2p shell level, which means the atom is stable. And then oxygen, they're not stable, so that means that the electrons are repelling, and the electron cloud expands slightly
Due to the
propulsion.
So as you can talk about Coulombic attraction, you can also talk about Coulombic repulsion. As the force of repulsion increases, they tend to spread out in the available space. And so since they do have a whole entire lobe of a p orbital to spread out, and it causes a little bit of an expansion of that orbital that we would normally expect to be following the trend.
Good. Okay, so here is a graph of the elements in the periodic table, and you can see how the atomic radius increases from right to left and then down the columns.
And you guys can see it's hard to see, on the back row where the hydrogen is, it's kind of small back there, and then it's even smaller. I'm looking at the second row now, from lithium over to fluorine. It's small. It gets smaller from left to right, but we know it gets larger from right to left. All right, thank you. All right, questions on atomic radius right now? Let me go back this time.
Yep.
2 slides. Right here. So this, I tried to paraphrase because I had to jump in with this group, so Riley wasn't all by her lonesome. So some of the stuff they have on their slide, I maybe didn't mention entirely, but we're videoing right now too. But I was paraphrasing it so that you understood shielding effect as an entire example, and how does that reflect in the atomic radius. Okay, ionization, or ionic radius people now? Thanks, guys. So here we go. Everybody kind of reset. If you have your computer out, put it away, be respectful. And I'm going to put the timer right here, guys. Oops. Here. Put that when you guys are ready.
Do we hit the start button?
Okay,
cool. All right. Hi. I'm Jack. This is Vinky, Sean, and Jacoby, and our group did the ionic radius of an atom. The ionic radius. The ionic radius is the distance between the nucleus and the outermost electron of an ion. So it's slightly different than the atomic radius, as it has slightly different rules, but we'll get into that a little bit later. There are specific trends. They're a little bit shaky, but they tend to decrease across the period, going right to left. All of the measurements are dependent on the ground state of the ion, and shielding is also incorporated into this idea, just like in the atomic radius. By having a greater number of orbitals decreases the attraction between the electrons and the nucleus.
Okay, so for cations, say we had a neutral lithium atom with 3 protons and 3 electrons. So if we were to take one of those electrons away, creating the +1 charge, it would, well, the lithium nucleus would still have a 3+ charge, but there would only be 2 electrons around it. And since there is less electrons on the outside, the atom is now smaller, and therefore there's less shielding. And so that's why the ionic radius is less than the atomic radius. Okay, and so it's
Sorry, I want to be back with that question. Go back for me. You said less shielding. Is that what you meant?
there's no shielding.
Shielding is the number of energy levels between the nucleus and the valence shell.
So there's not an outer shell anymore, and so therefore the 2 electrons get pulled easier to the nucleus, which is positively charged. All right, and so it's pretty much the exact opposite for the anion. So, for example, if we had a neutral chlorine atom, and we added an electron, it would have the -1 charge. So if you look at the electron configuration for it, it would be Ne in brackets. It would be neon in brackets 3s2, 3p5, but since we added the electron, it would be Ne 3s2, 3p6, and because of that extra electron, it's going to get bigger. And so the electrons will repel each other more, and therefore the cloud is going to expand, making it bigger than hence the ionic radius is bigger than the atomic radius.
Right, so to retouch on a key point of our presentation, the difference between the ionic radius and the atomic radius. In the case of cations, the ionic radius is smaller than the atomic radius, and in the case of anions, the ionic radius is greater than the atomic radius. For our Coulombic attractions, for weak bonds, the ionic bonds with bigger atomic radii have weaker bonds due to the smaller magnitude of attraction between the electrons. Ionic bonds with smaller atomic radii have stronger bonds due to the larger magnitude of the attraction. So because of this, the Coulombic attractions between the nucleus and the electrons are strengthened by the small radii and weakened by the larger radii.
Here's some quick examples, obviously, just to reinforce what we've been saying this whole time. With the gaining or the losing electrons for cations, they get smaller, and the gaining makes it bigger.
All right, so charge product relating to lattice energy. Lattice energy is defined as the attraction between, the measure of the strength of the bond in an ion. So the higher charge product means that the breakdown of the lattice is less favorable. So the higher charge product means that the lattice energy is going to be greater, and the opposite is true for lower charge products. So for example, calcium fluoride compared to lithium fluoride, calcium fluoride's charge product is greater, so calcium fluoride is less likely to have that breakdown of lattice energy than lithium fluoride is.
And
Yes.
so on your notes, if it says bond dissociation,
Yeah, mark that out and put lattice.
Yeah.
So we were debating about the terminology to use, and so can you guys tell us why you opted to use this instead?
The term lattice energy, compared to bond dissociation energy, ionic bonds aren't actually bonds; they're attractions. So, therefore, you don't need to dissociate the bonds; you have to dissociate the lattice energy in between each bond.
And they are speaking about the two factors, the size on the previous slide, where they're talking about how size of the atom or the ions related to weakness or strength of the bonds that those ions would form. They're not talking about individual ions, they're talking about, of course, a pairing of ions. And here they're talking about the charge product. So they're talking about both factors that affect lattice energy. As an application of this, I just want to interject here while we're here. Calcium fluoride is less likely to dissociate than lithium fluoride, for example. How does that relate to solubility rules or solubility of a compound?
Calcium fluoride is less soluble than lithium fluoride because all alkali metals are basically soluble.
Okay, so all alkali metals are soluble. You're right, and you're saying it's less soluble, but why?
Because the attractions are greater, so it's less likely to be broken down.
Right, the attack of the water molecules ain't going to do nothing because you're going to continue attacking calcium fluoride. It's not going to dissolve. It's not going to dissolve. What does that do to its KSP value? Decreases it. You see there's some connections coming back.
Yes.
Thank you. Keep going.
okay. So across the period, at first it will decrease while the period is cations, and then once you get into anions, it increases sharply because the ionic radius is bigger for anions, and it continues to decrease throughout the period. And then down a group, the ionic radius generally tends to increase. So, yeah, so here are our measurements. So that's hydrogen going right, that's the period, and then going down. So you can see right here, it's decreasing for anions. And then when you get to like a cation, or it's decreasing for cations, when you get to anion, increases.
Yeah, it's worth noting that these trends aren't actually like totally trends. They're just kind of like
They follow their own trends through cation.
It's a pattern.
It's a pattern.
yeah.
So yeah, the graph shows it better. So like cations and then anions, and then it goes back down.
This is also important to note. The noble gases, your neon, argon, and krypton, those do not form their own ionic radius because they do not form their own ion because they're in a stable state already. So they can't like gain or lose an electron, because if they gain or lose an electron, they won't be stable as they already are. So therefore, they don't form any ions, meaning they don't have an ionic radius.
Yeah, and group 8 is has no values. All right, so in our reading, there's something about isoelectric ion series, and it's important to understanding ionic radius. So basically, isoelectronic ions are ions that have the same amount of electrons. So examples are oxygen, the oxygen ion, fluorine, neon, sodium, magnesium ions, and these all have 10 electrons, but the oxygen atom is bigger than the magnesium ion because the ionic radius decreases as charge increases, because there's more nuclear charge in the magnesium ion because there's more protons, so there's more nuclear charge pulling in electrons, and there's less electron repulsion that causes the oxygen ion to be bigger than the magnesium atom. So if you ever get like a test question that would ask, which ion would be better, you would say the one with the less charge. If they have the same amount of electrons, the one with less charge, because there is less nuclear charge.
All right, so to basically conclude and wrap up on everything we said, the ionic radius is the distance between the nucleus and the outermost electron in a shell, or in an ion. The cation's ionic radius is less than the atomic radius. That's because taking away electron causes the repulsion to decrease and therefore making the ion smaller. And for anions, it's the opposite, because adding an electron in causes the electrons to repel from the nucleus and making it bigger. Coulombic attractions between the nucleus and electrons are strengthened by small radii and weakened by large radii. And then, is there any questions for us? Yes, ma'am.
Can you go back to your table? Okay, right there. Can you guys tell me why it increases down group 1?
There's more. Reason it decreases down is because there's more, increases. I apologize. There's more protons in each of the nucleus. So that's kind of.
Because they have more sublevels, and then
Basically.
Yeah.
That's why we had to do atomic radius first to understand why energy levels building an atom influence the size. Well, same thing. You didn't really take away, 8 shells to point 1 shell, though you still had a lot of energy. Sorry, anybody have some questions?
Oh yeah, mark out bond association.
I'm glad you guys are utilizing your notes, because this will help you with your questions later. Thanks, guys. Everybody clap. Thank you. Thank you guys for being loud and proud. My people at home, the viewers at home, will need to hear this. Very good connections. That's what I was looking for. Ionic stuff has a lot of connections to make. You guys ready? This will be our last one for a moment, then we'll take a break, and then we'll come back and do the other 2, okay? Stretch break, stretch break. I can't do yoga, these pants are too tight, so you guys are gonna have to do it by yourself. Give me a second. Get everybody get a stretch break. Awesome.
So Emily,
I do not. Someone's birthday. Someone's birthday.
When is to be born?
my birthday.
Is your birthday?
Okay, and to Chloe, Arshia, and Duru. Go for it. Oh, set your timer. You see the timer right there? Should say 10. Go ahead. All right, go ahead.
Okay, so we did ionization energy. Yay!
Okay, so this is the graph, and it's not tilted right, it's tilted to the side, but this is hydrogen, that's helium over there. And as we go to the right, it increases in going up, and also goes up in that way.
Okay, so ionization energy is the amount of energy that an atom needs for an electron to be free from its orbits. So, and the trend increases up into
Okay, so as far as Coulomb's law goes and Coulombic attraction basically states the attraction between positive and negative charges, which then relates to electron binding energy. Because electron binding energy is the binding between the nucleus and its electrons in sublevels, which then relates to ionization energy because it's the amount of energy it takes for those electrons to be released from the nucleus shell. And then the size of the atom relates to ionization energy because of the bigger the atom, the more space there is between the nucleus and its different sublevels. So it's going to take more ionization energy if it has a bigger atomic, no, less ionization energy, bigger atomic radius, because it's not going to have as much attraction to the nucleus. And that also ties into valence electrons because that's the outermost shell, so those are more likely to be let go. Nuclear charge, as the nuclear charge goes up, ionization energy goes up because, yeah, it does because of the attraction between the nucleus and the electrons. So as far as the shielding effect goes, and on this side the penetration effects, those are two kind of opposites. So the shielding effect has to do with the number of electrons in the inner shells. So if it has a greater shielding effect, it's going to have lower ionization energy, as we stated prior, with the binding energy and the size of the atom. No need to see this.
Take a quick pause for a second. Can someone repeat one of the main things she just said?
Ionization energy decreases as size increases because you have a lesser attraction between protons and electrons, so electrons can be rotating off the nucleus, there's less force.
Perfect. So that's about the size, and then that's related to the shielding effect, which you said. Somebody else? Savannah, give me something about shielding effect.
It increases upper group and to the right.
Okay. The shielding effect?
Oh, the shielding effect.
You guys gotta listen really carefully.
Okay,
Our she's
so
talking real fast. Yeah.
So the shielding effect decreases ionization energy.
Thank you.
Yeah.
So more shielding, less attractions from the nucleus, lower IE.
Yeah.
Thank you. All right, keep going.
and this has to do with the size of the atom, which then relates to shielding effect because of the number of electrons in the inner shells. So it's going to have a greater shielding effect, lower ionization energies because those electrons are more likely to be let go. Whereas the penetration effect, which is sort of the opposite, the ionization energy needs to remove an electron, so it decreases in the sublevels order. So this has more to do with the exact sublevels versus comparing it to the outer shell, which is what shielding effect does. Penetration just focuses on the specific sublevels. And as far as electron configuration goes, atoms that are more stable, so if they're half filled or fully filled, are least likely to lose an electron, which is why they're going to have a higher ionization energy because it takes more energy to let go of the electron. So if you compare two atoms, let's say we compare something group 1 to group 2. So let's say sodium. Sodium is half filled, so it's less likely to be ionized because it's a stable state as compared to magnesium. No, that's a really bad example. Okay, so sodium compared to aluminum. So sodium, half filled, it's more stable, whereas compared to aluminum. So it's going to have a higher ionization energy because it's less likely to ionize or lose those electrons compared to aluminum, which is easily ionized and also easily.
I'm going to interject here. So I can't let fake news come out of here. So aluminum has a higher ionization energy according to your diagonal trend. It's across the same period, it has a higher ionization energy. However, that's the honors chem easy way of describing it. They're getting ready to talk about exceptions. They're trying to give you examples without talking about exceptions, but I think the exceptions are the most important part of this. So remind your brains about a minute.
Yeah, that's another bad example.
Let's keep, don't do any more examples.
Okay. These are just ionizations. No.
So as to expand upon their penetration effect, do note that S block penetrates the nucleus, P block less so, and that's what they're going to talk about with their exceptions. Keep going.
Yeah. Okay, so as far as ionization energies go,
Yeah. Okay, so for the first ionization energy, that's the energy required to remove the highest energy electron from a gaseous neutral atom. And the second is the energy required to move a second electron from a slightly charged atom, like sodium plus. And then for the third, ionization energy, that's the energy required to remove the third electron from a doubly charged gaseous cation, like sodium plus.
So it's basically adding an electron and, okay, well not adding, but adding ions, and then as you add ions, the energy it takes increases.
How so?
Because in order to do that, you'd have to, well, first for the first one, you're removing, well, no, I lied. You're removing an electron from a neutral gas atom, so you have sodium with a plus ion, and then you're taking the singly charged cation to remove another electron.
Pause. What's the difference of that energy?
It's greater. It's a lot greater because
Like a lot. Like, why that much?
because sodium is less likely to be ionized to begin with. Sodium.
Nope. Guys, I don't want to do your presentation for you. Can somebody else up there add to this? Why is such a significant jump in energy? Wait. Sodium's like, I don't give a crap about my electron. It gives it up pretty easily. 400, 500 kilojoules, it's fine. Sodium doesn't want its electron. It has one valence electron. Second ionization energy is 5,000 almost. Do you want to add to this?
I was going to say, why? Because it takes more energy to get it off because the repulsion between the electrons is less once you get them away. So that way, the Z is increasing as like you have less of the protons or the neutron.
And you're pulling an electron from the from the inner core energy, the energy level. So the first one's coming from a valence shell, which is pretty far away, low attraction, not so hard, 500 kilojoules. 5,000 comes from an inner core electron, which is a whole energy level closer to the Z, due to the shielding effect, and it's already charged, which is kind of what we were just talking about with the repulsion. Continue.
Okay, for the exceptions. So if a element has a half-filled or completely filled subshell in the electron configurations, the ionization energy will be higher than predicted because the atom is more stable, so it will take more energy for the electron to be freed. And if the atom if removing one electron achieves a half-filled or completely filled electron configuration, which would make it stable, the atom will have the lower ionization energy than predicted. So it just depends on their electron configurations and how many electrons they have in their outer shell.
So can you explain that graph right there? Can you explain it with those specific examples that you deemed important?
So in the
So explain to me in layman's terms what's happening on the graph for P to S. The ionization energy is
decreasing.
okay. Normally not what would occur, right? The trend is it increases as you go across the period, and we see the exception. Why is it easier to take sulfur's P electron than phosphorus's P electron?
Because it has an extra, it's not, this one's half filled, so it's more stable, and this one has an extra, well, this one's filled completely, so it would make the charges, like,
So the extra repulsion, we need to finish this graph. So the extra repulsion that sulfur's shell fills, right there they have circled, the extra repulsion leaves it a little bit inherently unstable. So when you remove, it's like, please take this extra electron. When you remove it, it doesn't require as much energy simply due to the repulsion within that orbital, like you were mentioning. Phosphorus, it's not that it's holding on to its electrons better, it's just kind of, as a relative comparison, sulfur is easy to remove because of repulsion. That's inherent. Keep going.
Okay, so exceptions in period 3A and 6A, they have a lower ionization energy than expected because of valence electrons at a higher energy level are a further distance away from the nucleus, so the attraction of the electrons is lowered, so it's easier to remove those electrons.
You said that, and higher energy level farther away from the nucleus? Explain it to me. Because it's not, energy level is not the term. Because it's group 3A and 6A. Give me two examples from periodic table 3A and 6A.
So 3A would be
Aluminum. Okay.
So aluminum, which is fine, my aluminum thing to work out. But aluminum, and then 6A would be sulfur.
Okay. Why are these not following the trend? They're not. It's not because of energy level. They're all in third energy level, or they're valence.
Because aluminum only has one electron in the outer shell.
Which shell?
In the electron configuration, it only has one electron.
And it's 3p.
It's 3p.
Okay. And then sulfur has
4.
4. Okay. So we're going to add to that thought in a second. 3p1 versus 3p4. Keep going.
Yeah.
All right. Thank you. Because atomic radius and thank you, ionization energy are the most. I'm not going to say I have favorites, but they are one of the more important themes to discuss. Let's do a quick activity with this to talk about why the trends occur a little bit more in depth with what they were saying with the P and the S, because that's where nuclear penetration with the S orbital makes most sense to talk about. So you guys have the packet I just gave you. It has a graph on it. Okay, so on this graph, we're going to actually annotate this and why. On the back. So let's annotate these trends in accordance with what their graph, basically, you see this graph right here. We need to understand why it's not a linear line from 5 up here to like 25. Why does it have a jagged edge there? Okay. So, talk in your groups for a moment first. I want you to annotate why the jagged edges occur on the ionization energy line. Talk about why that would be.
So it's like it's really hard to pull. Well, for us, yeah, for ionization energy, it's really hard. That's why because like then it's like the alpha attractions that the activity charge and the cooling interaction between the off nucleus.
Guys, focus. All right, label this on your axes or on your graph itself. What's this first one indicated? Hydrogen. Okay, and this is ionization energy versus atomic number, because you guys have your graph in front of you, can see this. Hydrogen and then helium, right? Okay, so this is ionization energy. First off, you already knew that trend from hydrogen to helium, it should be increasing. Why is helium higher than hydrogen? No, it's not because it's noble gas. Okay, that's a fact, not a reason. You guys need to learn how to justify things.
Because I don't know how to explain. I have no idea that much.
Thank you, Zeph. That's me. If you're not saying nuclear effective charge, shielding effect, size usually gives a decent explanation. You're not thinking about the reason. You're thinking about facts. Okay, so this hydrogen to helium, this one has 2 protons, this one has 1 proton. They're both in the same first energy level, right? Okay, so this has higher nuclear effective charge, meaning it has a higher or stronger Coulombic attraction for its outside of energy level. Then we drop down to lithium, right? And then beryllium, labeling this on your chart. I didn't print that out for nothing. It's not just a pretty curve. I want you to make sure that you can read these, because sometimes they'll give you graphs like this and they'll say, why is this jump occurring between blank and blank? So lithium to beryllium to boron to nitrogen to oxygen to neon. What should the trend be if we were just going with our factors? Should just be increasing, right? But then we see these wiggles in the middle, and that's what their exceptions were explaining. 3A and then 6A. So we should see, as we do, an increase from lithium to beryllium. Why? Say again? Zeph. Okay, we're still talking about the same period. Lithium, beryllium, boron, nitrogen, oxygen, neon are all in the second period. So that means that they have two energy levels, 1, 2. But lithium is 1s2, 2s1, right? Beryllium is 1s. I'm just going to do the valence if that's okay, because I'm running out of space. Beryllium is 2s2, right? What's boron? So 1s2, 2s2, 2p1. Why does it not trend upward? Anybody?
Because there's only one electron in that orbital, so it's easier to remove than having a full orbital.
So comparatively, you're saying it's easier to remove a 2p electron?
There's only like one. The orbitals.
I'm rephrasing it so that we're right. Okay. So I'm trying to use your guys' basic knowledge and put it in a term that would be an appropriate explanation. Okay, this is because you guys struggle with explanations, and we're in qualitative land for a while. All right? Yeah, okay. So 1s2, 2p1 versus this 2s2. The s block, you're writing this down, s block electrons undergo nuclear penetration, meaning that this 2s and this 2s, being the same electrons, when they undergo nuclear penetration, the s orbital basically attracts more to the nucleus than the p orbital does. So if you're closer in proximity to the nucleus, is it easier or harder to pluck that electron off? Harder. So p orbital electrons are farther from the nucleus, or aka don't undergo nuclear penetration. So hence they are easier or require less energy to pull off the atom. Yeah. Say again? Nuclear effective charge is about the number of protons. Nuclear penetration is talking about how the orbital electron cloud just happens to shrink into the nucleus with more force. It basically stays closer in proximity to the nucleus. But you guys know what these shapes are, right? What's an s orbital look like? Sphere. What's the nucleus look like? What's the nucleus look like? A sphere. Okay, so when you have your s orbital and you have your nucleus, they're basically equally being pulled in on all accounts. So hence it has this great field of attraction across the entire perimeter. Whereas a p orbital, like this, right? How in the heck does that get attracted to the nucleus? The nucleus is here in the middle someplace, but it's attracting in, but not as much as close to it in proximity, so it doesn't have as much nuclear penetration. Yeah.
So nuclear penetration is like directly related to the atomic radius?
No. Nuclear penetration is only related to the ability of s orbitals to feel a stronger attraction to the nucleus than p orbitals. So you're basically comparing orbital types, nothing about radius. Yeah. So that's a good point. Nuclear penetration refers to this is what they just said. You guys have this in your notes. S undergoes higher nuclear penetration than P, then D, then F. So highlight that or star that from their group's information. Nuclear penetration, S is greater than P. Okay, so that's why we see this wiggle here, because we've essentially entered P block, and P block electrons are less attracted to their nucleus than s orbital electrons. Yes. Okay, then boron increases in the trend. Great. And then, oh my gosh, we see this again. So this is 2s, 2p.
3.
Oh, I must have missed. Oh yeah, carbon's right here. There you go. There's carbon. Sorry, it follows a trend. I was like, where did I go? So 2p3. All right, and then we have 2s2, 2p4. Okay, we explain between 2a and 3a with nuclear penetration because orbitals now become different. How do we explain 6a as an exception?
It says that whenever you have your electron configuration, there's now 2 electrons in that little.
Orbital.
Yeah, sure. And so now they will repel each other. It's easier to get off.
Okay, so electron repulsion allows for oxygen's first electron to be pulled off a little bit easier due to the instability electron repulsion causes. Hence, if you're trying to become stable, if you can get rid of an electron, it's going to be easier to do that than a half-filled p sublevel as this P3 represents. Okay, how do you explain a 2A exception? How do you explain, a 2A to 3A? Nuclear penetration. How do you explain a 5A to 6A exception? Electron repulsion. Periodicity means a pattern exists. You'll see that over and over and over and over across the entire periodic table. That's why I'm not doing it more. Okay? Yeah? Shake your heads or something? Okay. On the other one, it's not as much. I'm actually not going to do that now. All right, so pause for a moment. Go to question 2. It says reciprocation activity periodic trend, which is going to be question 2. Answer 2A, B, and C. It should take you about 3 minutes. 2A, B, and C. 2A, B, and C. Yeah.
Did you say that you can't use the words
Break
break bonds?
bonds?
Like you can't say the word break bonds. Like you can't use that phrase.
You cannot use that phrase for internuclear forces. What are you trying to use it for?
Like, I don't know what to say. But like that's what I'm thinking. But like, can you visualize it?
Overcome contraction. Is that what you're going to say? Thanks. Overcome attraction.
So for shooting,
Say that one more time.
the pull, the stronger pull between the nucleus and electrons will overcome more shields to pull the electrons down.
That's confusing.
There's like this bullet that I want to say that's all.
And I'll correct it on the spot if I need to. I'm trying to really listen to you guys' words because you guys are just like, and I'm like, I'm pretty sure they just said 3 wrong things, and that's why I'm calling you guys out on the spot, okay? So it's not me being mean, it's me trying to make sure you're not misinforming people. All right, look on the board for me for a second. I'm giving you an example of element X and Y. Can you tell how many valence electrons X has, Jack?
Well, are you talking about like in comparison to Y?
Nope, I just want to know how many valence electrons. I could give you 15 data sets, right? But I'll just look at X's data. First ionization energy is 200, and then second ionization energy is 400, and this is kilojoules per mole. and then you see 4,000. Can you tell me somebody tell me how many valence electrons this has? A couple of you go. 2, why? So relatively easy to get those electrons from the first and second ionization. And then, holy cow, I must be on an inner core electron trying to take that electron. Next one, why? Why? Right, so relatively easy to get the first electron off the atom, and then sequentially much, much, much higher. There is not a number you look for a large jump. The large jump also varies. It's not just doubling, it's like a lot more. I don't know what a lot is because it's different for every atom because it's different first ionization energy for every atom. But if you see a huge jump, it's usually like, I'm an inner core electron. Huge jumps, I'm an inner core electron. That's going to give you insight into what charges it could form and so forth. All right, I'm going to have you guys stand up for a second, go talk to another group, and then I'm going to have my last 2 groups go, and then we're close to done here, okay? Can you go grab some water, get up for a second? I'm just making sure you get a break from the groups, remember. So electronegativity is next. Yeah, take a quick, you need to take a quick phone break to see if somebody has texted you, because I heard that. You look up your thing. I heard somebody's phone go off. It could have very well been mine. Just keep getting updates from my AP Chem class. Are you guys okay without Lucas? I'll tell him you don't need him.
Lucas was going to be.
Alright, so
I told him that.
10, and then
The 47 kilograms.
let's go, Levi. Excuse me. Alright, I am waiting on that group, but I really don't have a lot of time left. There's 30 minutes in class, you guys need 20 of it, so
I'm going to start.
go holler at him.
I'll get that guy.
Do you guys look like cancer? Do you guys look like cancer on me? Yeah, you guys look like cancer. Okay, please.
And then I guess I can say for now, look on the board for homework. It says complete. That's a generic word for today. Complete periodic trends of our fused problem set or multiple choice. I want you to get as much done on your problem set. I'm sorry, not problem set, on your FRQs as you can, because that's going to practice your explanation skills. The multiple choice ones that you started, there weren't very many you could do outside of like quantum and subatomic particles. We're going to be reviewing some of these tomorrow and the next day in class, kind of throughout the rest of this week. We're almost done with atomic structure basics, so that's why make a note to self. You need to try as many of those while this is fresh, so that you can see what you feel comfortable with in terms of atomic structure. Yeah.
Okay, so looking at these graphs, like, I know you can't say that the atomic radius are related, but could you like understand how they yeah, like you get a practice.
That's why I'm going to this week.
And then this.
All right, when we are starting, set the timer and go.
Where's the started?
Start button.
Alright, we did electronegativity. So basically electronegativity is the ability for an atom or the nucleus of the atom to pull in electrons, whether that be valence electrons or free electrons. Okay, so it's measured in the Pauling scale, and it affects Zeph because obviously Zeph is the pull of the protons in the nucleus towards the valence electrons. Coulombic attraction. So fluorine is
the most electronegative atom because it's the smallest. So that means that the protons are closer to the electrons on the outside. And that results in a larger Coulombic attraction, which shrinks the atom. Alright, so obviously, like I said, the size of the atom matters, so the smaller the atom and the more protons it has, the higher the electronegativity. So why is fluorine the most electronegative as opposed to like chlorine, which is on the same group? Well, fluorine only has one sublevel that's shielding its protons from the electrons. So its electron configuration is 1s2, 2s2, 2p5, so it only has to overcome the shielding of 1s2 to pull in electrons on the outside, as chlorine has two sublevels to get past for shields. So this is the electronegativity trend. It obviously goes to the right and up. Francium is the least electronegative with 0.7 on the Pauling scale, and fluorine is a 4.
Pause. Go back for us. Are they going too fast, guys? You okay? Right. Note the highest number. What is it?
4.
4. That is the Pauling scale. It's a little different than some other ones. What are some key things you might see here? Talk to your group.
Noble gases do not have electronegativity because they are already at octet, so they don't want electrons overflow.
So this is just another representation of it. You can see how it increases up there and to the right.
Oh, do you want to do that? Okay, so there is a theory called the diagonal trend theory. It's not an exact pattern, it's more like a correlation. Metallic atoms, there's like a correlation between the electronegativity between this and this. As you can see, since it increases right and up, like that diagonal, and that diagonal line might have similar electronegativity values on the Pauling scale. So why? I'm going to see references. Go back. Okay. So. Okay, why is this a thing? Because lithium has less protons than, say, magnesium, which is on the diagonal line for this theory. So magnesium, the additional protons that magnesium has compared to lithium kind of make up for the extra shield that it has to overcome, and that's why there's a trend. Yes?
I have an important point to make with that, and this will apply to all groups. There is a more significant change in the shielding effect down a group than the nuclear effective charge across a period. So that's why this diagonal effect occurs as well. So there's the magnitude of ZEP changing versus the shielding effect changing is not linear, it's not the same. And that's going to cause some differences and why you have to read some of these a little differently. Thanks.
You do it this way. Okay. All right. What the first thing that electronegativity can tell us about bonds is the type of bond, which is whether you have the 3 nonpolar covalent, polar covalent, and ionic. And the way we can determine that is by the difference between the 2 atoms that are bonded together. I feel like you have something to say. If it's 0 to 0.5 and their difference, it's going to be nonpolar covalent. 0.6 to 1.9 is going to be polar covalent, meaning that they're still covalent, but like you have a positive side, negative side. And if it's 2 and above, it's considered an ionic bond. That's pretty much that. And over here, whenever you have electronegativity differences, you'll usually have, if it's polar covalent, you'll have a positive side of your atom and a negative side. And from this, you create a dipole moment, which I'll get to in a second.
So, why is it important to know how to predict electronegativity? Because similar electronegativity, when you have 2 atoms that are about to form a bond, means that they have similar ZEF. And similar ZEF means, since ZEF means that it's the pull of the protons to the outermost electrons. If they have similar ZEF and they both pull them in, then they're going to share electrons and form a covalent bond. As opposed to higher electronegativity difference, meaning an atom with high ZEF and an atom with low ZEF that are going to create an ionic bond because one electron is going to go over to the other atom.
Okay. You have dipole moments, which are created when you have polar covalent bonds, which I'll sum that up here. And basically, these are a measure of just how polar covalent a bond is. It's not an actual thing. It's just a representation. And so, how you calculate it is the charge magnitude of the atoms times the distance and direction of the polar covalency. So, like, if you had a positive here and negative down here, that would take into effect in your equation. Did you talk about the ions? No?
So they're talking about some stuff with our bonding section, which is coming in a couple days. So this prior knowledge, I'll expect you to have a little bit on, like with the polarity differences. So, and that's the application of their trend.
And just for another example of why it's good to know electronegativity and what this can help us predict, the first example that came to our head was making batteries, because we just did that, and you can figure out based on your values which elements will be likely to give electrons to which other elements, which ones react the easiest, be most effective.
Right back to electric. Yeah, so their electronegativity differences does relate to reduction potentials quite a bit as well. Thank you guys for introducing bonding as well.
Yeah.
Save best for last. Best for last. So this is a suggested pattern trend, but they'll get into that. This one has a interesting look to its graphs. All right, so I need you with me for 10 minutes, okay? And then we'll get our break at the end. All right, so in terms of electronegativity and electron affinity, theirs are related to some things that we're coming to very soon. And Lucas is here in spirit. Thank you. That's your time. Set it for it's just nice that you guys can see it versus me giving you like countdown exactly.
Okay, so the definition of electron affinity, it's the change in the energy in a neutral atom in its gaseous state when an electron is added to the atom to form a negative ion. So that it's talking about like a neutral atom and then the amount of energy it takes to add an electron to that atom. And it's usually exothermic because so all the values are negative. So the magnitude of the values determines the strength of the the attraction to the nucleus. So that talks about the electron affinity. So it's kind of like the opposite of ionization. Okay, so it's kind of like the opposite of ionization energy, because if you look at this equation that we have for electron affinity, so you have chlorine gas and you're adding an electron to that gas, and then you get Cl minus, and then it's exothermic, and then the ionization energy, it's that, but it's flipped, and then you can see that the ionization energy is endothermic.
And the general trends, though they're not really solid, but the first one is that it decreases down a group, and that's because the atomic size increases, so the electrons that are attracting to the nucleus are further away from the nucleus, which also causes Coulombic attraction to decrease. And then it increases across a period, and that's because there are more protons added, so the nuclear effective charge increases, and it creates a greater attractive force.
So the added electrons in the electron affinity, it feels a greater attraction to the nucleus because of the larger ZEF.
And then nonmetals also tend to have a more positive electron affinity than metals.
Can I ask you to elaborate on nonmetals have more positive affinities than metals? Meaning you're saying metals will be negative, right? Generally?
Yeah.
Why nonmetals, endothermic, and metals, exothermic?
It has to do with the valence electrons. Non-metals tend to be, with electron affinity, they tend to be, I think it's a exothermic?
Look at you have a positive right there, it's endo.
Yeah.
Bottom bullet.
Endothermic,
Endothermic EA.
So they lose, I think they lose the electrons easier. So,
Right, affinity means to add electrons. So let me backtrack. This is a conversation I had with this group because the terminology here, they have to balance both sides in one phrase. It's difficult. If I release energy, that means one thing. If I gain energy, it means another thing. If I release energy, what is happening to the stability of the atom? Increasing. You need to write that down for yourself. Exothermic means atom is becoming more stable. Exothermic, atom is becoming more stable. So then hence endothermic would be less stable.
Because it's gaining energy, yeah. I mean, like, all of the electron affinity occurs because it's attempting to, like, become more stable. Like, you can see that in the exceptions as well, and you can see that in, like, what's happening here as well.
Right. So and I thought it made a lot of sense to talk about it there because you guys are going to talk about the factors, how it changes across the period, and it's going to be really apparent to know.
this is our graph. That's hydrogen. So with this graph, as you can see, the trends aren't really normal. It does kind of decrease down the groups. It increases kind of.
So it's not as apparent down the groups. It's not, but the more significant trend is across the periods. But you do notice that, like, the noble gases are very, very small. They're basically insignificant. And group 2A and group 2A, 3A, and group 2A and 3A are insignificant as well. And I think, yeah. So, like, if you look at the exceptions, like, you would expect it to, like, keep just go up across the period, but the actual trend is that, for example, nitrogen, it's lower than, the electron affinity is lower than carbon, and then if you look at neon, it's very small, and then beryllium, it's also supposed to be really small. So with neon, the reason that there's an exception, it's because adding an electron would disrupt this stability and push it up to the next energy level, and as well as it would push it up to the S block, and then that would release significantly less energy. So, like, most noble gases require putting in energy to add an electron. So for the exception in 5A, the example that we used was nitrogen. So the electron affinity is lower than carbon's due to its electron configuration. So if you look at nitrogen's orbital notation, then it's half filled, and it's like it's half filled and it's stable, but as soon as you add or you remove one, so if you remove one, the attractions, so the repulsion, or like I think adding one makes more sense. So then there's, when you add one, the electron repulsions, it makes it more unstable, and then that is what makes it easier for it to add an electron.
To which one?
It makes it easier to add an electron to the one that's more unstable, because you're attempting to gain stability.
And so the hard part about this one is they have to explain it as endothermic and exothermic. So going back to your chart, go back to that graph, sorry, that previous slide. So we have the back one, okay. Oh, nope, right here. That's, you guys see carbon drops and carbon to nitrogen drops, right? Explain it from this. Is is this representing magnitude of an exothermic value?
It's representing atomic number.
I know, but electron affinity is a number. It's a
number.
exothermic number
Yeah.
in many of these cases.
Yeah.
So carbon has a higher magnitude exothermic release of energy than nitrogen.
Yes. So it's a more negative number, but the magnitude is larger, meaning it's more exothermic.
So carbon's releasing energy a lot to make it more stable as it gains that additional electron in its p shell.
Yeah.
Whereas nitrogen is already half-filled. It's not going to stabilize as much as carbon did. Hence, it has a lower magnitude exothermic number.
Yeah.
Do you guys see the complexity of that statement? Okay. Keep going.
So then if you look at 3A, group 3A, that's the example there is beryllium. And then the electron affinity is lower there because to add an electron, it would have to jump from the 2s to the 2p. And then there's also, you have to consider electron shielding. So adding an electron there, it doesn't take as much energy because adding an electron there doesn't take as much energy because you've got the 2s, it's already filled, and that's like blocking the attractions from.
I want to add to this, because I'm sure Lucas would be saying this, and I'm saying this with him in spirit. 3A, electron affinity is lower. Likely it's less endothermic because this is a metal, right? So why is this less endothermic? Why does it require less energy to put an electron in a p shell than in an s shell? Because a p shell is farther away from the nucleus. An s shell is closer to the nucleus, aka nuclear penetration, right, group? So that's going to cause a difference in proximity, which would require less energy to put in, because there's less force of attraction there. Kind of.
Okay, yeah. I think that's on, yeah.
Hooray! Good job, Ruth! So, there, we have a question.
So it's like the same since the 2s and 2p levels go just as far away from the nucleus, would it take the same amount of energy to put an electron in S?
Putting something in S likely will, depending on what it is, if you're putting in S, you're probably putting it in a metal. It will probably require more energy to do that because many times these are metals less likely to accept electrons. The definition of a metallic character is that it's likely to lose electrons. So if you're closer to the nucleus, yes, electrons are more stable. However, there's a lot of pent up energy between the nucleus and unwanted electrons. So I think that's why they'll sort of bump in there that as well. Perfect timing, guys. Okay.
That's actually cool.
All right, so overall, good job. In case, and I will have the other groups present, I need to ask you guys, let's switch modes. Let's get a multiple choice. Pull out that multiple choice because I know that's probably about much brain power you left for me today versus free response. You have your packets? Okay.